Hello and welcome back at the FinetLink channel. Now we will study about VLAN. Just imagine that you are in charge of a very large conference and there are so many people all over who want to share a common interest and some who also have simple and special expertise. Imagine if each expert who wants to present their information to a smaller audience had to do that in the same large room with all the other experts and their smaller audiences. Nobody will be able to hear anything. So in this case, you will need to find separate rooms for all the experts and their smaller audiences. The same is even for virtual LAN, or as we call that, VLAN. That is kind of similar and what the VLAN does in a network. VLANs are created at the layer 2 to reducing or eliminate broadcast traffic. VLANs are how you break up your network into smaller networks so that the devices and people within a single VLAN are communicating with each other and not having to manage traffic from other networks. The network administrator can organize VLANs by location, who is using them, the type of the device, or whatever category is needed. So what we will study here in this material will be the objective to implement VLAN and trunking in a switch network. So first of all, we will have an overview about VLANs where we will explain the purpose of VLANs in a switched network, and then we will explain how to configure switch port to be assigned to a VLAN based on requirements. We even will explain how a switch forward frames based on the VLAN configuration into multi-switch environment. Then we will configure a trunk port on a LAN switch. And lastly but not least, we will configure dynamic trunking protocol. So we will discuss in the first part about the overview of VLAN and the VLAN in multi-switch environment. So let's continue with the first topic. Organizing the network into smaller networks is not as simple as separating screws and putting them into jars, but it will make the network easier to manage. Virtual LANs, or as we call VLAN, provide segmentation and organizational flexibility in a switched network. A group of devices within a VLAN communicate as if each device was attached to the same cable. VLANs are based on logical connection instead of physical connections. Here it is shown a figure where the VLANs is switched in a switched network enable users in various departments. As you can see, we have the IT department, we have the Human Resources Department and Sales Department. And those need to be connected to the same network regardless of the physical switch being used or location in a campus LAN. VLANs will allow an administrator to segment network based on factors such as function, team, or application without regard for the physical location of the users or devices. Each VLAN is considered a separate logical network. Devices with a VLAN act as if they are in their own independent network, even if they share a common infrastructure with other VLANs. Any switch port can belong to a VLAN. Unicast, broadcast, and multicast packets are forwarded and flooded only to end devices within the VLAN where the packets are sourced. Packets destined for devices that do not belong to the VLAN must be forwarded through a device that supports routing. Multiple IP subnets can exist on a switched network without the use of multiple VLANs. However, the devices will be in the same layer 2 broadcast domain. This means that any layer 2 broadcast, such as an ARP request, will be received by all devices on the switched network, even by those not intended to receive the broadcast. A VLAN creates a logical broadcast domain that can span multiple physical LAN segments. VLANs improve network performance by separating large broadcast domain into smaller ones. If a device in one VLAN sends a broadcast Ethernet frame, all devices in the VLAN receive the frame, but devices in other VLANs do not. Using VLAN networks, administrator can implement access and security policies according to specific grouping of users. Each switch port can be assigned to only one VLAN except for a port that is connected to an IP phone or to another switch. But what are the benefits of VLAN design? Just you have to know that each VLAN in a switch network corresponds to an IP network. Therefore, VLAN design must take into consideration the implementation of a hierarchical network addressing scheme. Hierarchical network addressing means that IP network numbers are applied to network segments or VLANs in a way that takes the network as a whole into consideration. Blocks of contiguous network addresses are reserved for and configured on devices in a specific area of the network, and it is even shown here in this figure. And there is a table about the benefits and the descriptions for the VLAN. First of all, the VLAN has smaller broadcast domains, because by dividing a network into VLAN, reduce the number of devices in the broadcast domain. And as you can see here in the figure, there are 6 computers in the network, but only 3 broadcast domains. Another benefit is that it improves the security, where only users in the same VLAN can communicate together, and they can communicate together without the service of a router. Another thing is that they improve IT efficiency, where the VLAN simplify network management because user with similar network requirements can be configured on the same VLAN, and VLANs can be named to make them easier for identifying them. And as you can see in the figure, VLAN 10, it is called the faculty. We have VLAN 20 as students and the VLAN 30 as guests. Another benefit is that they reduce the cost, where the VLAN reduces the need for expensive network upgrades and use the existing bandwidth and uplinks more efficiency, resulting in cost saving. They have better performance because smaller broadcast domain will reduce unnecessary traffic on the network and improve performance. And the last benefit is that simple project and application management, because VLANs aggregate user and network devices to support business or geographic requirements, and having separate function makes managing a project or working with a specific application easier, as it is shown as an example for application in e-learning development platform at the faculty. And there are different types of VLAN. VLANs are used for a different reason in modern networks. Some VLANs type are defined by traffic classes. Other types of VLANs are defined by the specific function that they serve. We have a default VLAN, where the default VLAN on a Cisco switch is usually the VLAN 1. All switch ports on the VLAN 1 are assigned for the switch unless it is explicitly configured to be on another VLAN. And by default, all the layer 2 control traffic is associated with this VLAN. Important facts for VLAN 1 is that all the ports are assigned to VLAN 1 by default. The native VLAN 1 is VLAN 1 by default, and the management VLAN is VLAN 1 by default, and VLAN 1 cannot be renamed or deleted. And if we use the show VLAN brief output, all ports are currently assigned to the default VLAN 1 here in this switch. No native VLAN is explicitly assigned and no other VLANs are active, as you can see. Therefore, the network is designed with the native VLAN the same as the management VLAN, and this is considered a security risk. Another kind of VLAN is data VLAN, where our VLANs configured to separate user-generated traffic. They are referred to as user VLANs because they separate the network into groups of users or devices. A modern network would have many data VLANs depending on organizational requirements. The voice and network management traffic should not be permitted on the data VLAN. And here are listed all these characteristics of the data VLAN. We have even the native VLAN. And the native VLAN, user traffic from a VLAN must be tagged with its VLAN ID when it is sent to another switch. Trunk ports are used between switches to support the transmission of tagged traffic, especially on 802.1q. Trunk port inserts a 4-byte tag in the Ethernet frame header to identify the VLAN to which the frame belongs. A switch may also have to send untagged traffic across a trunk link. Untagged traffic is generated by a switch and may also come from legacy devices. The 802.1q trunk port places untagged traffic on the native VLAN. The native VLAN on a Cisco switch, as we mentioned, is the VLAN 1. It is a best practice to configure the native VLAN as an unused VLAN, distinct from VLAN 1 and other VLANs. It is not unusual to dedicate a fixed VLAN to serve the role of the native VLAN for all trunk ports in the switch domain. Another kind of VLAN is the management VLAN. A management VLAN is a data VLAN configured specifically for network management traffic, including the secured shell, telnet, HTTPS protocol, HTTP, and the protocol that are listed here. But by default, VLAN 1 is configured as the management VLAN on a layer 2 switch. And remember that you have to change the management VLAN different from the VLAN 1 for security purpose. And lastly, we have even voice VLAN, which is a separate VLAN needed to support voice over IP traffic. And the characteristic of this VLAN is because it's assured bandwidth to ensure voice quality, transmission priority over the other types of network traffic, ability to be routed around congested areas on the network, and delay of less than 150 milliseconds across the network. To meet these requirements, the network has to be designed to support voice over IP. Here it is a figure where we have the VLAN 150 is designed to carry voice over IP traffic. and the student computer, which is PC5, is attached to a Cisco IP phone, and the phone is attached to a switch 3. PC5 is in the VLAN 20, which is used for student data. VLANs would not be very useful without the VLAN trunks. VLAN trunks allow all VLAN traffic to propagate between switches. This enables devices connected to different switches but in the same VLAN to communicate without going through a router. A trunk is a point-to-point link between two network devices that carry more than one VLAN, as you can see here. So a trunk is a point-to-point link between two network devices that carry more than one VLAN. As you can see, at this link goes data of VLAN 10, 20, and 30. A VLAN trunk extends VLANs across an entire network. Cisco supports protocol for coordinating trunk on fast Ethernet, gigabit Ethernet, and 10 gigabit Ethernet interfaces. A VLAN trunk does not belong to a specific VLAN. Instead, it is a conduit for multiple VLANs between switches on the route and the routers. A trunk could also be used between a network device and a server or another device that is equipped with the appropriate 802.1q capable network interface card. By default, a Cisco Catalyst switch, all VLANs are supported on a trunk port. In the figure, as you can see, it is highlighted link between the switch 1 and switch 2, the link between switch 1 and the switch 3. And those links are configured to transmit traffic coming from VLAN 1, 10, 30, and 99, which is the native VLAN across the network. This network could not function without the VLAN trunks. When a switch receives a broadcast frame on one of its ports, it forwards the frame out all other ports except the port where the broadcast was received. Here we have an animation where the entire network, here it is configured in the same subnet for 172.17.40.0/24. And there is no VLAN configured here. As the result, when the faculty computer, which is a PC1, sends out a broadcast frame, switch number 2 sends that broadcast frame out of all its ports. Eventually, the entire network receives the broadcast because the network is one broadcast domain. Let's see. So is the PC1 that is sending the broadcast, and as you can see, all the devices in the network will receive that broadcast because the switch 2 will forward all of its ports except the port F011 where the frame comes. And VLANs are associated with and configured on individual switch ports. Devices attached to those ports have no concept of VLANs. However, these devices are configured with IP addressing and are members of a specific IP network. This is where the connection between VLANs and IP network is apparent. A VLAN is the equivalent to an IP network or kind of subnet. VLANs are configured on the switch where the IP addressing is configured on the device. Here there is an animation where we can see that the same network now has been segmented by using two VLANs. Faculty devices are assigned to the VLAN 10 and student devices are assigned to VLAN 20, as you can see. When a broadcast frame is sent from the faculty computer, which is the PC1, to the switch 2, the switch will forward that broadcast frame only to those switch ports configured to support the VLAN 10. So let's see the animation and see the difference between the network without VLAN and network with VLAN. So in this case, the port F01 can forward broadcast frame for VLAN 10 and VLAN 20, even though port F01 to switch 1, port F03 at switch 1, and port F03 at switch 3. So you see that the port that compromised the connection between switches switch 1 and switch 2 and between switch 1 and switch 3 are trunks and have been configured to support all the VLANs in the network. When switch 1 receives the broadcast frame on the port F01, switch 1 will forward that broadcast frame out of the only other port configured to support the VLAN 10, which is the port F03. When switch 3 receives the broadcast frame on the port F03, it forwards the broadcast frame out of the only port configured to support VLAN 10, which is port F011. The broadcast frame arrives at the only other computer in the network that is configured in the VLAN 10, which in this case is the faculty number PC number 4. When VLANs are implemented on a switch, the transmission of unicast, multicast, and broadcast traffic from a host in a particular VLAN are restricted to the devices that are in that VLAN. The standard Ethernet frame header does not contain information about the VLAN to which the frame belongs. Therefore, when the Ethernet frame are placed on a trunk, information about the VLANs to which they belong must be added. And this is the process called tagging, where we add a header with 4-byte tag insert within the original Ethernet frame header, specifying the VLAN to which the frame belongs. When the switch receives a frame on a port configured in access mode and assigned to a VLAN, the switch inserts a VLAN tag in the frame header, recalculates the frame check sequence, and sends the tagged frame out of the trunk port. And as you can see in this figure, the VLAN tag control information field consists of the type field, the priority field, the canonical format identifier, and the VLAN ID field. At the first field, there is a 2-byte value called the tag protocol ID, and for the Ethernet, it is set to hexadecimal as 08100. We have the priority, user priority, which is 3-bit value that supports level or service implementation. And then we have the canonical format identifier, which is 1-bit identifier that enables token ring frames to be carried across the Ethernet links. And then we have the VLAN ID, which is 12-bit long and is the VLAN identification number that supports up to 4096 VLAN IDs. And as for the native VLAN, we have a native VLAN for trunk leads, which is default to VLAN 1. When an untagged frame arrives on a trunk port, it is assigned to the native VLAN. Management frames that are sent between switches is an example of traffic that is typically untagged. If the link between two switches is a trunk, the switch sends the untagged traffic to the native VLAN. We have tagged frames on the native VLAN, where some devices that support trunking add a VLAN tag to native VLAN's traffic. Control traffic sent on the native VLAN should not be tagged. If an 802.1q trunk port receives a tagged frame with a VLAN ID, that is the same as the native VLAN, and it will drop the frame. So, when configuring a switch port on a Cisco switch, we have to configure devices so that they do not send tagged frames on the native VLAN. Devices from other vendors that support tagged frames on the native VLAN include Epiphone, servers, routers, and non-Cisco switches. And we have even untagged frame on the native VLAN, where when a Cisco switch trunk port receives a tagged frame, it will forward this frame to the native VLAN. If there are no devices associated with the native VLAN, which usually is not usual, and there are no other trunk ports, then the frame is dropped. The native VLAN, which is VLAN 1, is the default VLAN. When configuring an 802.1q trunk port, a default port VLAN ID is assigned the value of the native VLAN ID. All untagged traffic coming in or out of this port is forwarded based on the port VLAN ID. And for example, if you have the VLAN 99 is configured as the native VLAN, the port VLAN ID is 99 and all untagged traffic is forwarded to this VLAN. If the native VLAN has not been reconfigured, the port virtual VLAN ID usually is set to 1. Here there is a figure where the PC1 is connected by a hub to an 802.1q trunk link. And you can see that the PC1 sends untagged traffic, which the switches associated with the native VLAN configured on the trunk port and forward accordingly. Tagged traffic on the trunk received by PC1 is dropped. This scenario reflects poor network design for several reasons, because there is a hub which has a host connected to a trunk link, and it implies that the switch have access port assigned to the native VLAN, and it also illustrates that motivation of the 802.1q standard specification for native VLAN as means of handling legacy scanners. And as for the voice VLAN tagging, you need to know that a separate voice VLAN is required to support voice over IP. This enables quality of service and security policies to be applied to voice traffic. A Cisco IP phone connects directly to a switch port, and an IP host can connect to the IP phone to gain network connectivity as well. The access port connected to the Cisco IP phone can be configured to use two separate VLAN. And one VLAN is for voice traffic and the other is a data VLAN to support the host traffic. The link between the switch and the IP phone simulates a trunk link to carry both voice VLAN traffic and data VLAN traffic. There is a Cisco IP phone that contains an integrated 3-port 10100 switch, and the ports provide dedicated connection to the following devices. Port 1 is to connect the switch or other voice IP devices. Port 2 is an internal 10100 interface that carries the IP phone traffic, and port number 3 is access port, which is to connect a PC or other device. The switch access port sends packets instructing the attached IP phone to send voice traffic in one of 3 ways. The method used varies based on the type of traffic. The voice VLAN traffic must be tagged within an appropriate layer 2 class of service priority value. Access VLAN traffic can be also tagged with a layer 2 class of service priority value, and access VLAN is not tagged, which means that there are no layer 2 class of service priority value. Here there is a figure where the student's computer PC5 is attached to a Cisco IP phone and the phone is attached to the switch number 3. VLAN 150 is assigned to carry voice traffic, while the PC5 is in the VLAN 20, which is used for student data. And here in this example, there is an output for the show interface fast Ethernet 018 switch port. And as you can see, there are highlighted areas in the sample that show that fast Ethernet 018 interface is configured with a VLAN that is configured for data, VLAN 20, and a VLAN configured for voice, which is the VLAN 150. And that is the first part about VLANs, where we had an overview about VLANs and the VLANs in a multi-switch environment. Thank you for being with us. Do not forget to subscribe to this channel if you are new and hit the notification button for the new videos that will be uploaded. And if you like the video, share it with your friends. See you to the next session.